So today we're talking about piecewise functions. We define a piecewise function, guys. We define a piecewise function as a function that is defined by different formulas on different intervals. Those different formulas are the different functions, okay? And the different intervals are for domain, for the domain variable, but those are called the independent variable, aren't they? The one we're plugging in. This would be our x, or our domain, okay? Parts of our domain. And look what it says. It says for Formula 1, if use this domain for Formula 1. And Formula 2 will have the domain you use Formula 2 for next to it. And Formula 3 will have the domain you use Formula 3 for. So that tells you which formula to use based on which x you're using, okay? So let's look at an absolute value function. And here's an example of a piecewise function. Absolute value, if you remember, absolute value looks like this, doesn't it? It's a v. You all should remember that from Algebra 2. So on one side, you plug in an x, you get out an x. On the other side, if you plug in an x, it's negative, but then it becomes positive, so we make it negative x. And this is for if x is greater than or equal to 0, and this is for if x is less than 0. So you can see that this is function 1. This is function 1. And this guy is function 2. And this is domain interval 1. For function 1, okay? So now tell me, looking at that graph, is the function continuous? Remember what our definition was. Could I put my pencil down on the paper, draw that V without ever picking it back up again? So the answer is yes, it is continuous. So now, state the domain and the range. What is the domain of this function? How far to the left and right does this function go? All real numbers, right? So from negative infinity to what? Then it says, where is the function? Oh, that's the domain, by the way. So we say D equals. What is the range? What are all the y values for this function, guys? From where? Greater than 0. Is it on 0? So greater than or equal to 0. So my y values, my range is from 0 to infinity with a bracket on one side, right? Where is the function increasing? That's an interval, guys. Where is the function increasing? Where's it going uphill? From 0 to where? Yeah, from 0 to infinity. Now, where is it decreasing? Where is it going downhill? Negative infinity to 0. So on this side, over here, it is going downhill until it gets to 0, and then it flips and becomes to go uphill. So from negative infinity to 0. So now we've got something called the ceiling function. This is also called a step function. It's a type of step function. Ceiling function is defined as, notice that the ceiling function is here. It's got these little brackets at the top, right? But not the little bracket part at the bottom. That is the ceiling. So it says where x is the least integer greater than or equal to x, okay? So what does that mean? That means if we're looking at 1, and we have 1.5 here, and we have 2, If we are actually at 1.5, we will not stay at 1.5. 1.5 will jump to the next biggest integer. That is a ceiling function. In other words, it will jump to the next one above it, the ceiling being above, right? So what is the next integer above 1.5? 2. So this one will jump to 2. Now a floor function does the exact opposite. Notice where they are on the floor function. Floor function, the bracket part is at the bottom. So if the ceiling function jumps is greater than or equal to, what do you suppose the floor function is? Less than or equal to. So less than or equal to means that if we're doing the same thing, we're at 1, 1.5, 2, and we're looking right here. What is this one going to jump to? Yeah. Ceiling jumps up to the next integer, floor jumps down. So 1.5 this time will go to 1. So what are these two graphs going to look like, and how are they going to be different? It wants us to start at -3. Okay. So we're starting at -3. What will -3 be? -3 will be -3. Now, anything from -3 to -2 is going to do what? Sorry, -3 will be -3. What's going to happen? Anything between -3 and -2, if it is a ceiling function, what is it going to jump to? -2. Isn't -2 above -3? This is a ceiling function, so at anything above that, it's going to jump up to -2 until it gets to -2. Well, what's going to happen then? What's anything between -2 and -1 going to jump to? Guys, I have a feeling some of you aren't seeing this. You've got to look at it this way. We're at -3 here, -2, -1, and 0. So anything here, anything in the middle here, anything in here is going to jump to the next one up, isn't it? Anything in between here is going to jump to the next one up, right? Anything here jumped to -2. So at -2, now it climbs to -1. And then to 0. Anything between 0 and 1 is going to jump to where? Yeah. Anything here is going to jump to 1. So it looks like steps, doesn't it? With open on one end and closed on the other. And then we can keep going with this until we get all the way to what? From -3 to 3. So we stop here. That is what this looks like from -3 to 3. Now, how is this going to be different than the floor function? The floor function says what? It stays anything between, let's take this backwards. So we're going to start here at -3, and then -2, and then -1, and then 0, and 1, and 2, and 3, aren't we? So anything in here is going to go where? What you looking for? They're in that cabinet right there. Top shelf. On the right. Shelf. Get cabinet on the right. Up there in that top shelf to your right. To your right. Yep. Sorry. You're good. All right, guys. So what happens to everything between -3 and -2 if it's a floor function? Jumps down. It bottoms down to where? -3. So all of this goes to -3 until we get to -2. Everything between so at -3, it is indeed -3, and everything here until we get to -2. At -2, it's -2, isn't it? And then what happens between -2 and -1? Stays down at -2, doesn't it? And then at -1, it's -1. This is what I call an elevator. I want you to think about it. If you were between floors on an elevator, what are they going to do to get you to a floor? They're not going to raise you up, are they? They're going to what? Like gravity, bring the elevator back down, right? So this is your what I call an elevator function. Just think about it. If you got stuck between floors, they would let it fall back down to the floor just below, wouldn't they? Isn't that what this is doing? It's falling down to the floor below. That's why it's called a floor function. So this one does the same pattern, doesn't it? So how are these two different? The only thing really different about them is where the open and closed circle is, right? The open and closed circle is different. The ceiling function starts with an open circle and ends with a closed, but the floor function starts with a closed and ends with an open. Which makes sense, doesn't it? Ceiling, the closed should be on the other end because that's the direction it's jumping, isn't it? Floor, it should be on the other end because that's the direction it's jumping. It's jumping down versus jumping up. The jumping down or jumping up tells you where the closed circle is, okay? Does that make sense to everybody? What a closed and an open, what a floor or a ceiling function is. It's really just telling you where does it jump. Okay? So now, we've looked at 3 very special types of piecewise functions, but now how do we evaluate a function? How do we evaluate a piecewise function? This is actually a lot easier, I think, to figure out. When we're evaluating a piecewise function, all we need to do is figure out which piece of it we're using. So let's label these. This is function 1, this is function 2, this is function 3, isn't it? Would you agree? Just 1, 2, 3. So f of 12, this is our x value. This is our x. So what we have to do is figure out which one of those 3 functions does that x belong to. And to do that, we have to look here. These are our x's. So, does 12 belong with function 1, function 2, or function 3? How do we tell? We read that inequality. The first inequality says only the x's where x is less than 1. Is 12 less than 1? So it doesn't belong to that one. The next one says where x is between 1 and 3. Nope. What does the last one say? Greater than or equal to 3. So which one are we using? Function 1, function 2, or function 3? So we're using function 3. So we're going to plug into function 3. That's going to become 5 minus 1/2 times 12, which is what? 5 minus half of 12 is 6, right? So what is 5 minus 6? -1. So the answer is -1. Okay? So B, f of 2. Which function are we using? Function 1, function 2, or function 3? Function 2. All right, so we are using function 2 because 2 lies between 1 and 3. So we are going to have to plug into 2. Can I plug 2 into 2? Could I plug 3 into 2? No, it's just going to be 2, isn't it? Because it's a constant function. So guess what the answer is? 2. Easiest problem on here. All right, why don't you try f of -5? Which function are you going to use? 1, 2, or 3? 1. All right, so you're going to use function 1. So we need to plug in. And remember, what does absolute value do? It makes stuff positive as it comes out, not within it. Make sure you got the right answer. And guys, if you're prone to making mistakes in absolute value, use the absolute value function on your calculator. It's under math, right? Math, num, abs, and then put what's inside it in parentheses and just let it do it for you. All right. Did everybody get -8? Try f of 0 then. And check your answer. Yes. Absolutely. No problem. All right. So how are we feeling now about this? Can you plug into piecewise? Good. Try example 3. Why don't you try f of 6 and f of -3? Work with your table partner and make sure you're getting the same answer, okay? Or your seed partner. Okay. Maria? Got a schedule change, sweetie. Did everybody get the right answers? 11 and 8. Anybody have any questions? Are we good? Anybody need to see it work? Okay. So how do we write a piecewise function? Guys, first thing we have to do is figure out where our domains are and what type of function it is. Okay, so let's start with the domains. This is function 1, this is function 2, and this is function 3. You know why I work that way? We go from, how do we read functions? From left to right, just like we read. So what is the domain for the first function? That's what we're going to start with first, is filling in the domain. X is everything where? It's an open circle. Where? And everything below that, right? So how would we write that as an inequality? X is what? Below is what? Less than. Do we do equal to? Open circle or closed circle? Open, so it's just less than 2. Okay, so what are my values for the second function? From 2 to where? Five, right? So it starts at 2, ends at 5, and X is between that. The arrows always go the same way, guys. Do either one of these get the equal to sign underneath it? The 2, the first one, right? Because it is a closed circle here. All right. So where does the last one? What do we say for the last one? It starts at what? And goes to infinity, right? But we can't write infinity. So it's from 5 up. So how do we write that? Do we include a bar on it? Yes, greater than or equal to. All right, so that's the easy part. Hard part is now we've got to actually write what those functions are. So now we have to define what they are. One is linear, isn't it? How do we write a linear equation? Y equals what? Mx plus b. Do we know the slope? Could we find the slope? Yeah. Couldn't we find the slope between here and here? What is the slope? Down what? Down 1 and over 2? Would you agree? Literally just read it off the graph. So the slope is -1/2. So y equals -1/2 x. And then what was the y-intercept? What is the y-intercept right here? 5? So plus 5. So guess what goes up on our function graph? We don't put the y equals, we just put the x part. So what goes up here? -1/2 x plus 5. Okay? Now, function number 2 is the same value the entire time, isn't it? So function 2 is constant. That makes it really easy to write. What is the value that it is the entire way? 3, right? All we have to do is look over here to the y value, which right here is 3. So this thing is 3 that entire time. Now, the third function is what? It's linear again, isn't it? Y equals mx plus b. We can start with filling in the slope, can't we? What is the slope for this one? Down what over what? Down 1 and over 1, right? So it is -1 over 1. Problem is we don't have a y-intercept, do we? We don't have a y-intercept, so guess what we can do? We can plug in a point. I'm going to pick any point off this graph that I want and plug in for that x and that y. If I plug in for that x and y, what will that give me? If I have an x and I have a y and I have this, what's left? Yeah, the y-intercept, b. So what point would be the easiest on this part to pick? Yes? Why? Yeah, because it's where it touches the x-axis, and what's the y value there? 0. So we can plug in the 0.70, can't we? All right, so plug in the 0.70. So we're going to plug in a point. This is the 0.70. So we've got 0 for y, 7 for x. So what is b going to be? Well, 0 equals -7 plus b. You tell me. How do I solve for b? Don't make it harder than it is, guys, to say. One-step equation to solve. How do I solve for b? Add 7 to both sides, right? Okay, so what is b? B is 7. So now all I have to do is literally plug in y equals -1x plus what? Yeah. So if you don't know, so if it is linear and you don't know, then you can figure it out. So this is -x plus 7, isn't it? All right, let's try another one. The next one's actually going to be easier because it's going to use transformations. So let's look at this guy and let's figure out what is our, we've got 3 functions, don't we? So what is the domain of function 1? So this is function 1, function 2, function 3. Talk with your table partner and see if you can figure out what function, what the domains of the 3 pieces are. I heard somebody say it, right? All right. Looks like we're doing pretty good with those inequalities. Good. All right. So we should have gotten that the first function was less than or equal to 2. Everywhere from here down, right? The second function was between 2 and 5. And then this one is from 5 up. So x is greater than or equal to 5. Those are our 3 functions. Now, here's the cool thing. We can use, which one of these is the easiest to do? First, second, or third? 2. Because it's a constant function, so what is its constant value? -2, so that one booms, -2. Now, the nice thing is the first one is a quadratic, isn't it? We just did inequalities, or not inequality, we just did transformations. So this thing is normally at 0, isn't it? So instead, it's just dropped down 3, isn't it? So what would that look like as a transformation? X squared what? -3. Yeah. Now, the third one we're going to have to do again, like we've been doing. Y equals, like we just did the other one, y equals mx plus b. What is the slope of this function? Up 1, over 1, right? So what's the slope? +1. So it's just x, right? Do we know the y-intercept? Nope. So we just pick a point. Which point would you like to pick? It does not matter to me. Just pick one off of that. You want to pick the first one? Second one? Third one? I don't know. Here, how about we pick this guy? What is that point? That is the point what? 7, 4. So let's take and plug that in. 4 equals 7 plus b, right? Can we now solve for b? So what is b? Yeah. Subtract 7, and we get b as -3. So we're going to plug that back in. So what is my function? Y equals x what? -3. So what goes up here is x -3. Does everybody get it? Good. Okay, so now how do we graph a piecewise function? Well, we know how to do this. All we need to do is figure out, number 1, what type of function we have and where it goes. So the first thing we need to do is we need to draw in our boundaries. Where is my first boundary line going to be? And we're going to erase these when we're done, but they're like walls. The function can't go past this point. So the first function wall is going to be at -1. So I'm literally going to take and I'm going to say, okay, at -1, I've got a line right here that you can't go past. Where's the next one going to be at? So one's at -1. Then what? Next one's at 4. So the first function goes, so guys, I want you to understand, this is function 1, right? First function goes here. Second function's going to go here. And the third function is going to go in here. Okay? Does that make sense? Between the boundaries. All right, now we're going to use what we know about transformations to make this thing work. So the first thing I want to do is put the vertex in. The vertex, if you remember from transformations, the vertex goes where? It's normally at 0, 0, but this one shifts it where? 3 up and 4 to the what? Left? Okay, so this is 4 left and 3 up. So 4, normally from here we would go 1, 2, 3, 4, 1, 2, 3. So this is my guy right here. Now, if you're not sure what to do from there, all you have to do is actually plug in some points and see what it does. You get what I'm saying? This says it's a vertical compression by half, right? And it's flipped over. So we know it's going downward, don't we? So plug in a point. Plug in the point next to it in your calculator. Or better yet, you could throw this into your calculator and see what it does. But let's do this. What is this point? This is -4. So this is at -3, isn't it? Okay, so at -3, this is -3 plus 4 is 1, right? That's 1. 1 squared is 1 times the -half. -half. 1 times the -half is the -half, isn't it? So what is 3 plus the -half? Two and a half, isn't it? Okay, 2.5. So this would be at 2.5 right here. If it's at 2.5 on this side, don't parabolas mirror? Yes? So it's at 2.5 on this side, which means it's also at 2.5 on this side. Now, all I really need to know is what it does next at the border. So what is my border value right here? What is this border value? It's -1, isn't it? So let's plug that in. -1 plus 4 is what? Guys, you got a calculator. -1 plus 4. 3 squared is 9 times the -half. What do I get? Okay, plus 3. Okay, what is that in decimal form? -1.5. So right here it is at -1.5. So over here we are at -1.5, and we are going to, this is equal to, isn't it? So we are going to put a closed dot. Now, this should have a reflection on the other side, shouldn't it? So this was over 1, 2, 3. So this is over 1, 2, 3 this way. It should be reflecting over here, should it not? Does everybody agree? What does a parabola do? Goes up and comes back down, doesn't it? So this thing is going to come up to here and go back down. That's what this does. Now, what's it going to do in between? If we want to know what it's going to do in between, guess what we can do? Plug in what? Plug in values, can't we? Guys, if you're not really sure what it's going to do in between and you need to plug in values, you can put that in your calculator, can't you? Can we not put that? At -1, it's 5. And that is an open circle, isn't it? And do you see what you're going to do? So at 0, what's the value? Somebody has the table. What's the value? Table value at 0?
2.
So it goes to 2. At 1, what is the value? It's what? -1? It does not make, hold on. And this is closed. What was the value at 5? It's what? 1. So at 5, it's 1. At 6, it's what? 2. And at 7, it's what? 7, it's 3. And at 8, it was at 10. So look what happens. And why did I draw an arrow on that end? Because it's just going to keep going, isn't it? So does everybody see how we graph these guys? You can use your graphing calculator to help you graph them and throw the equation in, but the table really helps you plot the points. And notice we only read the table values off that were actually in the domain, correct? Okay. Converting absolute value function to piecewise functions, we are not doing this You don't have to be able to do that, not for this class, because you have a graphing calculator. I'm not going to ask you to do any of those. All right, so we're going to skip that. Applications, however. Applications are important when you do piecewise. As a matter of fact, this is really what we do piecewise for, is real world applications, okay? Real world applications say we have a piecewise. How do we know we have a piecewise? Because something acts differently over different periods of time. Anybody ever been to the parking deck over at the Huntsville Airport? Yeah, they charge you differently. Long-term parking, they charge you so much for the first day and then so much for the week, and then it changes again. Every time it changes like that, that's a piecewise function. How much they charge you up to a certain point. So let's look at this equation and see what we see. It says, in the land of Leibniz, a person filing taxes as single pay taxes pays taxes based on the following table. Notice how we figure out that it's piecewise, because the first income, that is our domain, isn't it? So if your income's from 0 to 30,000, you have a pay rate. Okay? From 30,000 to 65,000, so this is going to be domain 1. This is going to be domain 2. And this is going to be domain 3, isn't it? So if we're going to do a piecewise function, t of x, our domain for the first one is 0 at least and not more than implies not equal to, doesn't it? At least means it includes, but not more than is not equal to. So what is the second domain? Between where and where? Between 30,000 and, this one's included, but it's not included, excuse me, it's not included at the top. And then what's the last one? Yep. Included. At least means it's included, but not more than means it's not included here, is it? To 125,000. All right. So we've taken care of this, haven't we? Right? Okay. So now we got to find the function. Rate means multiply, doesn't it? So 15% is what in decimal terms? 0.15, right? So the function is 0.15 times x. That's what rate means. If, and now we're filling in. Now it says 4,500 plus 20% over 30,000. So we're going to start with 4,500, aren't we? Plus 20% would be 0.20, but we can't just put x. Over 30,000 means we have to put x minus 30,000. We have to take the first 30,000 out, don't we? Because we already dealt with it. Does that make sense to everybody? That this would be x minus 30,000. I hope so, because now we're going to do the last one. What is the last one going to look like being modeled off of the second one? It says 11,500 plus 24% over 65,000. So what are we going to start with? Plus what? 0.24 times. It has to be over what? The over 30,000. The over 30,000 led us to do minus 30,000. So over 65 means we have to do what? Yeah. And that's our function. So now it wants to know, evaluate the function to find the tax owed by a single person whose taxable income is $68,750. So if we're looking for T of 68,750. Which function are we going to use? 1, 2, or 3? Which domain does it fall in, guys? Domain 3, right? Over 65,000. So we literally just have to plug into our function. What does our function say? It is 11,500 plus 0.24 times what? What was our x? 68,750 minus, and that's a calculator problem. So what tax do they owe? Oh, yeah. So what ridiculous amount of tax are they going to owe? Yeah. Whew. I would not want to live in Leibniz. That's socialism for you right there. All your money. All right. Question. More applications. In August, Orlando Utility Commission supplied electricity to residents for a monthly customer charge of $8 plus 10.143 cents per kilowatt hour for the first 1,000 kilowatts used in the month, and then 12.146 cents per kilowatt hour for electricity over 1,000 kilowatt hours. Do we understand why we want a piecewise function here? We have one charge for using the first however many 1,000 kilowatt hours, and then another charge for anything above that, don't we? All right, so we need to know what is the cost. What is the charge for using 920 kilowatts in a month? So what is the base charge for the customer? $8. Plus, how many kilowatt hours are we using? What's the charge per kilowatt hour here? 10 cents, right? 10 point whatever. How do we write 10 cents as 10 cents in dollars? 0.10, right? So this becomes 0.10143 times what? Is this above or below 1,000 kilowatts? It's below, isn't it? So for the first 1,000 kilowatt hours. So how many kilowatt hours did we use? So 920. Boom. So what is the charge for your 920 kilowatt hours? How many decimal places do we round this? 2, because it's money, right? So 101.32, $101.32. So now, what do we charge for 1,500 kilowatt hours? This one is a base charge of $8, right? Plus and plus. Why did I just do plus and plus? 1,500 kilowatt hours means we use 1,000 kilowatts first, don't we? So we have to figure out what the first 1,000 is going to cost us, right? And then, how many kilowatt hours do we have above that? $1,500 minus what? So how many kilowatt hours are above 1,000? 500, right? So this is for the second 500 kilowatt hours, isn't it? So what is it going to cost us for 1,000 kilowatt hours? We just did this. 1,000 times what? Yeah, 0.10143. What's it going to cost us for the next 500? What's the charge for the next 500 according to our problem? Mm-hmm. So what does it cost us? 170 point what?
Or 174.45.
174.45. Not what I'm getting. Okay, 170.15. All right, guys. So now we need a regular C in terms of X. Let's turn what we did here into a function, piecewise function. We know my piecewise function is going to have two domains, isn't it? The first domain is going to be from 0 to what? And then everything greater than 1,000 gets the second piece, doesn't it? Now, we are going to model. I'm going to show you how we write this. This really represents the first 1,000, doesn't it? Would you agree? So let's use this and write it. This is going to be 8 plus 0.10143 times X, is it not? Does everybody know where that came from? I took out the 1,000, instead I put in, because it's going to be the same no matter what, isn't it? If it was 920, didn't we do the same thing? 8 plus 0.1043 times whatever it was? Yeah? So this just becomes, we just make this an X instead. And that gives us our first equation. Now the second equation is kind of interesting because the first one is kind of part of the second one, isn't it? Above 1,000, this amount is always the same, isn't it? So can anybody tell me what this amount is? What is 8 plus 1,000 times this? 109.43. So we're going to start with 109.43 and then add whatever this is, 0.12143. But we're not just going to put an X because this doesn't represent X, does it? What does this represent? What did we have to do to get the X there? Guys, to get this number right here, we had to go over here and take whatever the value was and subtract what from it? 1,000. So instead of writing just X there, we're going to write in X minus what? So do you see how working through it gives me the formula? And that would be my piecewise equation. So to figure out what a piecewise equation is, we plug some values in to figure out what the pattern is that helps us. So we took the first 1,000, this right here became this part right here, and then this, if we look at it, this right here became the other chunk, didn't it? So that's what we used. All right, guys, that is it. We've got 11 minutes left. So I would like to, if possible,